Well, hello everyone. This is episode number 18 in the ongoing saga of heliophysics in the universe and why you should care. Uh, Heliophysics, of course, is sort of the study of everything that the sun does to interplanetary space and to planets. It's everything from solar flares and how the sun produces its energy all the way out to how the solar wind interacts with the interstellar medium and with planets. So heliophysics is a word you're not going to find in the dictionary yet, but it sort of encompasses the whole 9 yards. Um, NASA likes to uh, group its pursuits in very simple terms. For heliophysics, the terms are what causes the sun to vary, how do the Earth and the heliosphere respond, and what are the impacts on humanity. We've kind of co-opted these three big questions in heliophysics and created a framework for heliophysics education, which basically takes these three questions and granularizes them a little bit so they can more easily map into the national science standards, which are given in the parentheses at the end of each of these sub statements. So anyway, tonight the easiest match is with 3.1. The sun is made of a churning plasma, causing the surface to be made of complex tangled magnetic fields. So it had the important term magnetic field, churning plasma, and complex. And that's about the closest match I could find in the standards to talking about the Earth's magnetic field, um, which anomalously is not a required topic in K-12 science education. The fact that the Earth has a magnetic field somehow got missing. But anyway,
So
one
Stan, send us
yes.
not to interrupt you. You don't have your headset on. And so when you turn your head, your voice fades in and out a little bit. So
Oh, okay.
I don't know
Well,
whether you want to put your headset
right.
on or you just want to hold your head still. I know that would probably be harder for you.
Okay. Let me talk more directly in the midline of the speaker. Does this
Okay.
work?
Yes, that's much better. Thank you.
Okay. Excellent. Right. Okay, so the Earth has a magnetic field, but one of the very curious things about Earth's magnetic field is it does not stay put. Now, when you think about the Earth and the Earth's rotation axis, that remains pretty fixed. I mean, it goes right through the geographic North Pole and the geographic South Pole. You can draw a line between those two through the center of the Earth. And that is the line about which the Earth rotates as a physical body. The Earth's magnetic field, however, is a much more sloppy and mushy kind of a thing, and it tends to follow a little bit the Earth's rotation axis, but it's not slavishly connected to it. And so that's what we're going to talk about and what some of the consequences are for that kind of non-traditional motion for the Earth's magnetic field. Amazingly enough, we know a lot about how magnetic fields are created and the very peculiar things that they do, not by studying the Earth, but by studying the sun. We've been studying the sun's magnetic field for over 2 centuries, and really for about the last century in some considerable detail. And we've learned quite a bit about how it produces its field. Um, Amazingly, the field that the sun produces comes from convective motions of the plasma just below the surface that we see. And these convective motions are of a particular kind that produce currents. And in the plasma, those currents produce magnetic fields, just as a wire carrying a current produces a magnetic field around it. Um, the thing is that when you have a plasma producing a magnetic field, there are a lot of different motions that the plasma can undertake. There are convective motions, there are motions called differential rotation, where there are actually changes in velocity as you go in certain directions within the plasma. All these things conspire to make the sun's magnetic field not a static thing that persists, for minutes, hours, years, centuries, but one which changes with a particularly cyclical pattern. And we know this as the sunspot cycle. And this is a kind of an animation of how we have used information about the vibrations on the surface of the sun to actually probe what's going on in the interior of the sun. And in particular, when you connect that kind of data with models that we have of plasma motion and how the motion produces magnetic fields, you can actually probe the interior of the sun as though you're using a CAT scanner or an MRI machine in a hospital, and it's a rather interesting process. Here's a kind of a film loop that shows sunspots coming and going during a sunspot cycle, and then there's a cutaway showing what goes on underneath inside the sun that produces the sunspots at the surface and also the magnetic field lines, which you see are getting wrapped up as the sun rotates, but also they shift in latitude in a periodic way that essentially traces the sunspot cycle, the 11-year cycle, very nicely. But more importantly, there's a 22-year cycle, which is the magnetic cycle. And I'm going to sort of describe that in just a minute. Um, it turns out that at the start of a particular sunspot cycle, uh, you can think of course, we know magnetic fields have polarities, and geographically, rotating bodies have hemispheres. They have a northern hemisphere and they have a southern hemisphere, and the dividing line is the equator. Okay. And the axis of symmetry between these hemispheres is, of course, the rotation axis of the body. Um, what you find is that when you look at the polarity of the sun's magnetic field in the northern hemisphere, it matches a north type polarity in the northern hemisphere. But then when you go 11 years later, which is one complete sunspot cycle, that northern hemisphere north polarity has been replaced by a northern hemisphere south polarity. And consequently, that north polarity that used to be in the northern hemisphere has migrated across the equator into the southern hemisphere. So every sunspot cycle, the magnetic polarity of the sun flips north south, south north, and then after 22 years, it flips back again to its original orientation, which is north south. Um, this is called the Hale magnetic cycle, and it's a fundamental cycle that's as fundamental as the sunspot cycle. And it is what you use if you want to understand and model not only how the magnetic field of the sun is generated, but how it changes over time. Not only do you have to get its local behavior to create the sunspot cycle, but you also have to get this 22-year cycle to come out correct. And the neat thing is that when you connect the rotation of the sun, the convective motions just below the surface, and the way in which a a process called the magnetic dynamo generates magnetic fields from this moving plasma. If you plug in the densities of the sun's plasma along with scales, you wind up with an 11-year sunspot cycle and a 22-year Hale cycle. So we're able to get a really good match between our theory and what we actually observe in the sun with this mathematical physical model called the magnetic dynamo mechanism. And so here is a kind of a cartoon sketch, just rendering it again. Each sunspot cycle, the sun's magnetic polarity flips from one hemisphere to the next, and then back again after 22 years. And you can see kind of how this plays itself out in this nice, colorful diagram. And essentially, what we can do with the magnetic dynamo theory and supercomputers is we can actually match the model calculations very nicely against this 22-year cycle and the 11-year sunspot cycle. So the implication is that we think we understand not only how the sun generates its magnetic field, but also the way in which that field changes over time, which is a very powerful predictive mechanism that we can now use. The caveat is for the sunspot cycle, although we get the 11-year cycle between maximum sunspots and minimum sunspots and then back again pretty well, we can't really predict how many sunspots you get at sunspot maximum or how many you get at sunspot minimum very well. So we can match the 11-year cycle. We can get that down, but we still can't get the actual amplitude. If there are going to be 256 sunspots or going to be 120 for a very weak cycle, we can't yet predict that in advance, even so much as one sunspot cycle in advance. We can get a general sense, but not an accurate one. And that is because of a very fundamental property of these convecting plasmas and the way they generate magnetic fields. Ultimately, this process is a chaotic process. Chaotic doesn't mean random. It just means that the dynamics are very complicated. They are not linear, as a mathematician would say. And that leads to behavior which is on the verge of not really being predictable. It can be quasi-predictable. So you can get a rough idea maybe within 20% of what the actual number is, but you can't get it bang on ever because of this chaotic process. And part of the problem that we have chaos in this mathematical model is that we can't measure the sun's magnetic field with enough precision in time and space to initialize the variables properly. Just being off by a little bit is enough to run your prediction forward and wind up with a very bad prediction after a few of these cycles. And we see this in weather systems and weather forecasting. We have this very rough 3-day horizon that is really hard to get over. And that's because for the Earth, we don't have enough measurement points in the surface of the Earth and at altitude to be able to constrain these very complicated mathematical equations to give us unique predictions. So we only get a range of predictions, and that range is determined by what we call this chaotic behavior of the equations when you don't put in accurate enough data or data that has high enough resolution to constrain what's going on mathematically. Anyway, on the sun, we've cracked magnetic polarity reversals since 1750. And of course, that with a little bit of math, we can count the number of cycles over that span of time, and voila, we get an average 11-year sunspot cycle for this kind of behavior. Now, you notice that the peaks vary in amplitude. That's the chaotic behavior that I'm talking about. It's very hard to predict exactly how high each of those peaks is going to be with a mathematical set of equations. So anyway, that's the problem that we have right now. We can pretty well figure out when sunspot minima are going to be and roughly when the sunspot maximum is going to occur, but we can't get the actual maximum sunspot numbers correct. The Earth also generates a magnetic field in ostensibly the same way that the sun does through this magnetic dynamo mechanism, as it's called. It turns out that although the inner core of the Earth is solid iron nickel, the outer region just above the solid inner core is a semi-liquid state, which means that because it's in a semi-liquid state, the inner part of it is at very high temperature near the inner core, and the outer part of it near the mantle is at a cooler temperature. So that means you can have convection currents flowing. Convection currents flowing in this outer core liquid iron nickel material. In addition to the convection currents, which would be sort of up and down in this diagram or left to right as little circles connecting the outer and inner region, you also have the Earth rotating in and out of the plane of this figure. And the coupling of the rotation with the convection leads to Coriolis forces. We see Coriolis forces when we have hurricanes spiraling near the surface of the Earth. They're deflected eastward or westward, depending on their direction towards or away from the equator. Same thing happens in the core of the Earth. And as a result, you wind up with these spirally kind of convection currents. And that means that the plasma is sort of circulating in a kind of a spiral pattern, which means that it can produce a magnetic field. And so that's how the magnetic field of the Earth is produced. But of course, since it's grounded in the fact that there's convection going on and Coriolis forces going on, it also means that this is a chaotic system, just as the sun's magnetic field is produced in a chaotic process. So that means that, to a certain degree, we can predict things about the Earth's magnetic field in the short term, but in the long term, this magnetic field is going to change in what appears to be a chaotic way. And so that's the thing you have to remember, that the Earth's magnetic field is not like a nail hammered into a piece of wood, that's a solid fixed thing forever and ever. It's more like, a lava lamp where you have globs of plasma moving up and down and rotating. And as they rotate, they produce magnetic fields. But as the globs change their shapes and densities, the magnetic fields also change their intensities and locations. So the interior of the Earth is more like a lava lamp, and it's a lot, and not at all like a toy bar magnet that you would buy, at the hobby shop. So don't think of the Earth's field being produced like a toy bar magnet. And that's a very, very common sketch that you see in textbooks, even through, college textbooks. If somebody wants to do a short, description of the Earth's core, they'll say, oh, well, it's like you have a bar magnet inside the Earth, and nothing like that at all. This model that I'm showing you here of dynamo theory is about 70 years old. So technically speaking, any textbook that you see, K-12 textbook or college textbook, should show something like this as a diagram. It should not show a bar magnet. And if you see a bar magnet, somebody's, either recycling an old image they used from previous textbooks in the new version, or just being, silly. Okay. Earth's magnetic polarity, just as the sun's polarity, reverses. And this has been going on for literally hundreds of millions of years, ever since the Earth's magnetic field started to become, very strong. What we have is we can actually identify when these reversals happens. In the mid-Atlantic zone, where you have the separation of two continental plates, you can actually take samples on either side of this rift zone. And if you go the same distance to the west and the same distance to the east, you're capturing magma that was extruded at about the same geologic time. And you can actually date the material using standard methods of geology. But you can also identify the intensity of the magnetic field of the Earth that was captured by the liquid magma at that time. It's like, have you ever seen those amber samples that have bees and ants trapped inside of them? Same thing with the Earth's magnetic field. When the magma cools, it captures the orientation and strength of the Earth's magnetic field within the crystalline structure of the material. So all you have to do is very carefully note the orientation when you sample the material, and then take it to your lab and date it. And so you can basically identify these polarity changes through studying these geological samples. Over 83 million years, geologists have been able to identify about 183 of these reversals. Math alert, sorry for the balloons, that's the best graphic I could find. 83 million years divided by 183 reversals. So the typical reversal time is about 450,000 years. Okay. The current magnetic reversal that we are in the future of is called the Brunhill. I can't even see this thing anymore. It's sort of hidden. All right, sorry. Yeah, it's identified geologically, and it happened about 781,000 years ago, and there hasn't been one since. So, sort of arguably, we're a little bit overdue for one. We've had a lot of magnetic excursions. In fact, we're living through one of those right now, where the Earth's field starts to weaken, and it looks like it's headed to zero strength. But these excursions, there have been about 20 of them in the last 700,000 years. So they happen a lot more frequently, but they don't lead to these polarity reversals. As you can see by the black bars, these reversals kind of happen very irregularly. They don't happen periodically. And once again, that's because the underlying process that's dictating these things is a chaotic process. All right. So these are not going to be periodic at all. They're going to be semi periodic, maybe 450,000 years is an average period, but there are going to be a lot of variation away from that number in general. So, with the magnetic dynamo theory, we can actually model the Earth's magnetic field and how it changes during one of these reversals. The far left shows the north polarity of the Earth in the northern hemisphere. Actually, I'm sorry, it's the south magnetic polarity of the Earth in the northern hemisphere. That's the current orientation. Currently, in the northern hemisphere, Earth's magnetic pole has a south type polarity. That's why the N on your compass needle points to that direction magnetically. South and north attract each other, north and north repel each other. So by convention, your N on the compass needle in the northern hemisphere is pointing to the magnetic pole of the Earth in that hemisphere, which must be a south type polarity to be consistent with that nomenclature. And that's how we identify the polarity of things, is simply by this geographic coincidence that started with, when people started using compasses for navigation, they would have a magnetized needle. They draw an N on the tip of the needle that was pointing towards the Earth's rotation pole. And that from then on became a north type magnetic polarity on that compass needle, which means that it has to attract a south type polarity in the Earth's magnetic field. So that's how that convention came about. So south type is blue and north type polarity is gold. And you can see that it starts out really nice, maybe a little bit wonky towards the equator. But then as we progress into slide number 2, 3, and 4, we see that the behavior of the magnetic dynamo becomes very chaotic. And geographically, you wind up with many different north and south polarity regions on the surface of the Earth. This would not be a good time to have a compass needle and try to navigate. And this kind of chaotic multipolar surface field of the Earth would go on for several thousand years. And finally, the far right is when the reversal has completed itself, and now we have a north type polarity in the northern hemisphere and a south type polarity in the southern hemisphere. And then the process will repeat itself during the next reversal cycle. Practically, what this means, for compass navigation, is that the compass needle in red, we want it to point, to the magnetic pole of the Earth in that hemisphere, in this case, the northern hemisphere. All right. But it doesn't exactly do that. And that's because the north and the south magnetic poles are not at all aligned with the north and south rotation poles of the Earth. In fact, because of the way this magnetic field is oriented in space, depending on where you are on the surface of the Earth, your compass needle is going to point many degrees away from the actual direction of the north geographic pole, which I show here with capital N sub G. And that delta is called the magnetic declination. Magnetic declination is something that's known to all navigators that use compasses. It's a number that appears on all topographic maps and navigation maps. Generally, it's not a single number, but has to be a set of lines and curves on the geographic map. That's because depending on where you're standing in latitude and longitude, this magnetic declination is going to be a different number everywhere on the surface of the Earth. Here's a kind of a simple example. Here's the magnetic North Pole, and here's the true North Pole. That little arc in there, sometimes in earlier map was called the variation, but it's called the magnetic declination these days. Mariners back long time ago completely knew about this little problem, but they also realized that if you compared navigation maps in Northern Europe that were like 10 to 15 or 20 years apart, the magnetic declinations would all be different. And so they had to redraw maps every 10 years or so in order that essentially they wouldn't run aground if they used the old compass bearings and the old magnetic declination to correct for where the actual true north is located based on your compass reading. So that was a real problem back then. Here's what the magnetic declination looks like if you plot it on a geographic map. As you see, it's not a single number, but it's a curve. Any location along that curve is going to measure exactly the same magnetic declination. If you look at the one that says 15 degrees east, that second line from the bottom, if you were standing at any point along that line, the magnetic declination would be the same. But if you were to step off that line, the magnetic declination would be different. And so whenever you're going camping in the high Sierras or doing any kind of a thing where you're going to be relying on your compass, you need to make sure you understand magnetic declination and allow for that with your compass. Your compass will not do that correction automatically. You literally have to dial it in on your compass. And depending on how far you're planning on going, I mean, if you're going to travel the Appalachian Trail, or the Pacific Crest Trail, which are thousands of kilometers long, you will have to make multiple changes on your compass in order to keep your bearings correct, because your magnetic declination is going to change continuously as you go north and south on the coast. Anyway, let's take a look at an example. In the high Sierras, the declination is 12 degrees east. That's what the magnetic declination is. That means that, as we see here, the magnetic pole is 12 degrees east of the actual true geographic pole, right? So here's what you got to do. If your map says that from where you're standing that your destination is a kilometer north, that's what you want to hike, what does your compass bearing have to be so that you're walking in the correct direction? Well, this is what your compass looks like, if it's in a standard orientation. It means that the true geographic north is 12 degrees to the east of magnetic north. So your compass needle in yellow is going to be pointing towards magnetic north, but true geographic north is 12 degrees east of that. So you have to go clockwise 12 degrees, and that's the bearing that you have to walk if you want to walk towards the geographic north, and you want to go a kilometer, to get to your car, for instance. So that's sort of what that calculation looks like. But here is the reality of it. Between 1600s and today, this magnetic declination has changed quite a bit as the magnetic poles of the Earth have wandered around. That little nexus of points that you see underneath the capital D That's the North Magnetic Pole wandering around, and the declination lines they have to move and change, as the magnetic pole changes. So you can see it's quite a complicated thing, and this shows why maps on the surface of the Earth that are going to be used for compass bearing calculations have to be changed literally every 10 years, so that the lines that they show here are reasonably accurate, and so that you can make the correct bearing adjustments. So anyway, magnetic declination changes because the North Magnetic Pole is not located in a fixed place on the Earth's surface. Here's where the magnetic pole was located in 1999, off in that fairly obscure little island in the Arctic. Um, but that's very different than what it is now. Here's a map of how the magnetic pole has wandered since 1840. You can see the blue line is kind of moving around, and then all of a sudden it takes off and starts really hustling away at light speed. um, so this points out a couple of things that the magnetic poles of the Earth don't wander in a uniform way. It's not like they orbit the geographic North Pole of the Earth. In fact, they have their own sort of behavior that's dependent on the way the currents are flowing in the outer core of the Earth during this particular epoch. And as I said before, that's a chaotic process in general. So the chaotic process also explains why it is that the motion can start out very slow, but then speed up and then slow down again and then move around geographically. I mean, all things are on the table, the way the magnetic pole moves and changes in time and space. So here's a kind of a fixed map that gives you a sense. The dots are spaced every 10 years up until 2000, and then every 5 years after that, because the rate of change of the position has been so quick. What we're now going to do is sort of to estimate how fast the magnetic pole is moving geographically. And to do this, we're going to look at two segments of this motion, one between 1962 and 1984. And we're going to use 1962 as the reference year at 0 kilometers. 1984, if you follow the blue line, has moved 160 kilometers away from its 1962 position. So that's entered in that third column. And then we're going to look at another segment between 2007 and 2020 and do the same thing. In 2007, we're going to call that 0. And 2020, the pole has moved about 600 kilometers away from its 2007 position. And now we are going to look and calculate some speeds, and we do that by simply dividing the distance traveled by the elapsed time in years. It's 22 years for that first segment. And we get about 7 kilometers per year for that period between 1962 and 1984. When we do the same thing for that second segment, between 2020 and 2007, we get 46 kilometers per year, which is about 7 times faster. So the motion of the Earth's magnetic field has geographically increased in speed by 7-fold in just a matter of about 50 or 60 years, which is quite an impressive change for a physical system that's as large as the Earth. So not only is the magnetic pole of the Earth moving geographically, but that motion is not uniform. So it's not it's not like the orbital motion of a planet around the sun. It's its own thing determined by the physics of whatever is going on in the outer core of the Earth during this particular period between 1960 and 2020. We can do something really interesting if we make geological samples of the Earth at different locations, we actually discovered that this polar wander has, of course, been going on for centuries, if not millennia. And this very complicated diagram that you see here basically shows the location of the North Magnetic Pole every 100 years. And you can see that it's sort of moved all over the place during this time. Um, so that is what is very interesting. The other thing that's interesting is that during even longer periods of time, we can also measure the Earth's magnetic field and its orientation over millions of years in time, not just a few millennia. And we get pictures that look like this. However, the kicker is that during this time, the continents have also moved geographically. Excuse me. The diagram on the left shows where the samples were actually made geographically today, along with their dates and the sort of location of the Earth's magnetic pole, as you can see, has sort of moved. But when we correct for continental drift, the fact that these continents have moved around geographically, and then make that correction, all of a sudden the curves fall right on top of each other, and we get a truer sense of what's going on in the outer core of the Earth. That right-hand diagram represents purely what's going on in the outer core of the Earth, where the behavior of the crust of the Earth has been literally subtracted out by allowing for continental drift. So that basically is sort of a summary of why we have polar wander, uh, how we measure it, the causes for it, and basically there's not a thing we can do about it. It's not like the ozone hole where we can actually try to do something about it. This is totally dominated by what's going on in the outer core of the Earth, which we can't even see directly. So we have to infer what's going on there by using very powerful physics-based mathematical models. But then we run into the problem that we don't usually have enough data to constrain these models properly. And so we wind up with chaotic behavior. And so essentially, um, being able to predict precisely what's going on with magnetic reversals is something which is not likely to really ever happen because we literally have to make measurements down at the source region, which is in the outer core, at resolutions of kilometers or better. And there's no way we're going to make measurements in the inner core of the Earth to that resolution. On the surface of the Earth, that's easy to do, right? Because it's accessible, but the core is not. So consequently, we're never going to be able to make precise predictions of when magnetic reversals will happen. But we can get at least a sense that they do happen, and we feel confident that we have a pretty good physics-based model for why they happen. So that's where we are right now. Anyway, so this sort of sort of the last talk in the series. We've sort of covered a lot of things in heliophysics in these 18 talks. I hope you've enjoyed this rather fast-paced introduction. And I wish you well in your future journeys and learning experiences. Thank you so much. And now I'm going to